Hello friends, today we are going to discuss about GoogleNet, Inception, V1 network and discuss about best practice toward GoogleNet, architecture and why need to go deeper and what happen if we go the deeper and how we can solve the problem if we go the deeper, and there are different kind of problem like vanishing gradient and computationally problems, so these kind of problem. So we need to go deeper because we need more accuracy. Here in two graph you find here there are if training, here the first in graph training error and the second graph training test error. In first graph training error increasing, yeah, and number of the iteration, after few iteration it model will be saturated and training stopped and learning stopped. So how we can go the deeper and and more objective of the GoogleNet of Inception V1. So the first objective, if the model is bigger, for the bigger model more prone it's to overfitting, and this is the particularly noticeable when the training data is small. And increasing the number of the parameter mean you need to increase your existing computational resources. So how these problem can solve? So GoogleNet come in the picture in 2014, and it was the first winner. It was the winner of the ILS VRC 2014 competition. That was GoogleNet, and that like problems of like image classification and object detection. So what we are covering here, first like one-to-one convolutional Inception module and overall complete architectures, and if we thinking about the training for the classifier, so that's we going to discuss about here. So before discussing Inception module, I'm going to discuss about one-to-one convolution, reason behind it, and why one-to-one convolution use and what happen if we are using one-to-one convolutions. So for the example, as an input, if you are taking 14 into 14 size of as an input and number of channels like 480, and we are convolving that input with kernel 5 into 5 kernel, and for example we need to output like 48 channel, so number of the filter will be the 48. So what will be the operation here? Then we are calculating the here operation, number of the operation. For example, we need 48 output, then 48 channel multiplied by 48 into 48 input, and number of and filter is 5 into 5 filter, and how many input channel is there? 480 input channel is there, then we have to 5 into 5 into 480 input channel, then we are getting here 112.9 million operations. So this number, just remember this number 112.9 million, this number we have to remember. Then we go, if we are using a middle layer, if you are using middle one-to-one convolutional layer, and what will happen if you are using this? So here we are putting one-to-one convolution, then we are going to 5 into 5 kernels. As a previous slide, like what output channel 48, and the in next we are, and here also we are same output channel 48. So here also input 14 into 14 and 480, output 14 into 14 and 48, and here also same 14 into 14 480, and output 14 into 14 48. So output about to similar, and this and similar output and channel is there. Then if you are using one-to-one, then what will happen here? If you are using one-to-one, then number of the operation for the one-to-one is the, if you are calculating this 14 into 14, number of channel is 16, then we multiply by 16, and 1 into 1, if number of channel for input 480, then multiply by 480, output is the 1.5 million operations. The second is for calculation for 5 into 5, then 14 into 14 and 48, 5 into 5 into 16, means 5 into multiply by this 16 input. So number of the operation is 3.8 million. So total number of the operation 1.5 and 3.8, then 5.3 million. You think about, just remember the previous 112.9 million operation, and now for the same thing we are getting and we have to do operation here 5.3 million. So which, and it's much smaller than 112.9. So you are thinking here, what happen if 1 to 1 convolution we are using here? It's a reduced dimensional. So it's reduced dimension also, and the accuracy also. And what happen if you reduce dimension here? So similar result we are getting, whatever result we are getting here, same result we are getting here. So that's the benefit of 1-to-1 convolution, and that's the magic of Inception method. So the finally conclusion, thus the Inception module can be built without increasing the number of the operation largely compared with one without 1-to-1 convolution, and another if 1-to-1 convolution can help the reduce of model size, which can be somehow help to reduce the orbiting problems. So we understood 1-to-1 convolution, then we can think about the Inception module. So what Inception? So I am going to discuss here for particular unit, one Inception module, one unit. Then we can connect this unit many times, and we can create a big Inception network. So what happened here? Like is a previous layer, like we can say starting as an input, and the next 1-to-1 convolution. So first I am going to discuss about here if without 1-to-1 convolution and with 1-to-1 convolution. So this slide for without 1-to-1 convolution, and this next I will go to discuss with 1-to-1 convolution. So without 1-to-1 convolution, if you go deeper here, then computationally it will heavy. Okay, but result we are getting the same. So but what is the difference with other network also? In previous network, like in 2014, below the 2014, like AnexNet, which is net, the convolution size is the fixed for the each layer. For example, they using only 3x3 convolution or 5x5 convolution, but we are use multiple convolution size. So that's the difference here. And what is the use of this convolution size or different convolution kernel size? That is the use cases, different use cases I will discuss later. So there's two difference here. Another network, like I'm adding here 1-to-1 convolution here, between that 3x3 convolution, 5x5 convolution. If I add here, then it will solve, it will reduce the dimensional. So 1-to-1 convolution is insert into the Inception module for the dimension reduction. So especially if they reduce dimension, and also is much smaller lot like operations, like multiplication, say whatever operation is there, is much smaller to the previous operations. So there are two benefits here. Next, so there are two benefits here. So this is called, this whole one unit called Inception module. Using this unit, we can create a big network. So in GoogleNet, we are creating, there are 22 layers of total. So everywhere they are adding one Inception module, Inception layer. So here you are unable to see what happening in particular, but for particular unit you are looking here for this, and again this. So all of the layer is the 22 layer total. And here you are getting middle of time, some fully connected, and some softmax, fully connected, then softmax, and you are looking here. So it's used for all the training. So this is the whole architecture, and in as a tabular format I am showing you how architecture will work. For example, input is whatever something, but if I are waiting output for first convolution, then 1-to-1 to 64, then max pooling layer, it will half the input size, like 56 between 64, then convolution, then increase number of the channel, then max pooling is reduce the size of input, and then we are putting here one Inception module here. That Inception module increase the channel here, and this Inception module is thinking like we have to go to the deeper here. And why need to go to the deeper here? I'm just taking the example. For example, this is dog image. It's a big image. You are looking here the big face here, and another dog image, that is a small image, and face also very small. So how we can go the deeper here? So how Inception module help for that? Here also we are taking different size of kernel network. For example, here 3x2 convolution, 5x2 convolution, 1-to-1 convolution. So for example, here for this picture, if the kernel size is big, then it's easily to capture that pattern also. But here if kernel size big, then unable to capture this pattern. So here we need to take a smaller kernel size, right? So in Inception network we choose different kernel size and we are going to the more deeper. So then we can extract the complex features also and classify perfectly. So that's power of the Inception network. And same here. So other is a network of 22 layer and followed by the average pool, followed by max pooling. So this complete network. So this all about the network and why network help for this kind of the complexity of a small object, a bigger object, how it will solve and how. So this kind of problem it solve. Now for auxiliary training, like I discuss about like somewhere we have we are using some middle part, some fully connected layer, some softmax. So it's used for the training. So how we can choose for auxiliary training, like 5x5 average pooling, 3 stride and 1x1 convolutional filter and 2 fully connected layer and softmax. So what happened here, like author, the paper writer, author I'm taking paper write, claim it can be used for combating the gradient variation problems and also providing the regularization. And whatever we are taking the intermediate softmax branches, that intermediate softmax branches is not used in so it's not used in testing, but inference time. Testing is not used in testing and inference time. It's used for the training times. So these are all about the auxiliary classifier for training. So these things today Inception part 1 we discuss about and implementations, and in next video I will come with the implementation of the Inceptions and how it solve the problem, like if we go the deeper. So thanks for watching my video.